All right, welcome everyone, and thank you for attending this remote high energy seminar. Today we will have a single speaker, Efrain Gatuzz, who was born in Caracas, Venezuela. He studied physics at the Central University of Venezuela and finished his PhD at the Venezuela Institute of Scientific Research. His thesis was on the analysis of the ISM using X-ray absorption, and he was supervised by Javier Garcia and Claudia Mendoza. He moved to Germany in 2015 to work as a postdoc at the Max Planck Institute for Astrophysics with Eugene Cherezov. His works included the analysis of X-ray gas distribution in the galaxy. He did a postdoc at ESO to work on the analysis of X-ray binaries with using high-resolution spectra with Dr. Maria Diaz-Trigo. He's currently a postdoc at the Max Planck Institute for Extraterrestrial Physics, working with Jeremy Sanders on the analysis of velocity structure in galaxy clusters using X-ray observations. Thank you for coming. Please feel free to start.
Thank you. I will share my presentation. There we go. And yes, it's a pleasure to be here. I visited CFA a couple of years ago, and it was a very nice place. When I was working with Javier Garcia, who is now in Caltech. I hope, I don't know, maybe next year we can go in person there. So yes, I got to talk today about my recent works on galaxy clusters. Particularly, we are studying the velocity structure in galaxy clusters using X-ray observations. Okay, so the first thing is why measuring velocities in the intercluster medium is important. So first we have that turbulent motions, particularly at large radii, affects calculation of hydrostatic equilibrium and cluster mass estimates. Here I am showing, for example, results from Lau 2009. And here you can see the mass contribution from thermal, rotational, and random motion. And as you move to the outskirts of the galaxy cluster, you can see how, for example, the mass due to random motion increase, and the contribution from rotational decrease. The thing is that thermal contribution is around 80–90% at large radii, but if you don't consider random motion of gas and turbulent motion, you will underestimate the mass of the cluster. So that's one of the reasons why it's important to consider the velocity structure. Also, we know that simulations predict a close connection between different parameters like entropy, temperature, density, pressure, and velocity power spectra. And this relationship is important to understand it too. For example, here I am showing the result from Mohapatra 2019. The plot shows the normalized X-ray luminosity function as a function of the velocity in the line of sight. And you can see here how for different velocities, the X-ray luminosity is affected. Of course, we have more parameters here like temperature, etc. But the velocity plays a role in the observables that we can measure in the galaxy clusters. Also, it is important to understand the velocity because motions will cause transports of metals within the intercluster medium due to sloshing and uplift of metals by AEM. So here I am showing results from Simonescu et al. 2008. This is an observation of XMM Newton of the Virgo cluster. And this is a map of the metallicity distribution. And you can see how in fact, this is iron abundance. So you can see how in some regions, the iron is enhanced. And the white contours correspond to radio contours. So you can see here, this is an arm, a radio arm. You can see a direct relation between the AEN, the outflows, and the abundance distribution. So motions will cause that, and it's important to understand the velocity structure because of that. And I have a fourth item here is that measuring velocities should directly indicate the sloshing of gas in core fronts, because there are some structures that could be observed, like for example these famous spiral patterns here. That is from a simulation from ASCA 2006. This is a simulation which only includes gas sloshing. So you can see these spiral patterns in the galaxy cluster. And these patterns, these sloshing features, can remain for several gigayears in the cluster dynamics. So these are some examples of why study the velocity is important. Now, there are ways to measure the velocity of the gas in the intercluster medium. We are talking about the hot gas, so we need X-ray observations here. One way to do it is by measuring line, broadening, and resonant scattering. So it has been shown that these measurements yields low turbulence motions. We are talking about 100, 300 kilometers per second. We can obtain more velocities too, but we can measure low velocities. These results here are obtained using the RGS high resolution spectra from XM Newton. So in general, this kind of complex technique to measure the velocities, and usually you will get upper limits for the velocities. But this has been done a lot in the last decade. Yes, as I say, the velocities seems to be low in general, the line broadening and resonance scattering measurements. But then we have Hitomi. Hitomi is allow us to directly measure random motion and Bull motions in intercluster medium because of the splendid instrument on board of the observatory. Here I am showing the Bull velocity field across the Perseus cluster. So color shows the difference from the velocity of the central galaxy and the velocity of the gas. In the core of the Perseus cluster, Hitomi measured line side velocity of 160 kilometers per second and between 30 and 60 kiloparsec of distance to the cluster core. And we have Hitomi found a gradient of velocity up to 150 kilometers per second. So the thing is that despite the obvious impact of the AEN in the cluster and on the surrounding intercluster medium, these results show that the Perseus core is not strongly turbulent. So such low level of turbulence indicate that it might be not fast enough to replenish heating. And although some waves or shocks could plausibly do this. Moreover, simulations have shown similar velocities when including gas sloshing or the AEN, the effects of the AEN. For example, here, top right panel, I am showing simulation from LAO 2017. These simulations includes AEN outflow feedback, and these magenta region correspond to the velocity obtained in the Perseus cluster by Hitomi, and the line correspond to the velocities obtained in the simulation for as function of the time scale. So, including AEN outflows, you can recover the velocities obtained in the Perseus cluster by Hitomi. But there are other type of simulation, or the class of simulation, if you want to say, that includes gas sloshing. And those simulations like this one from Suhone, also you can recover low velocities in the galaxy cluster. So we have here a play between both physical processes that can leads to low velocities in the galaxy clusters. Unfortunately, we will not be able to make further measurements. We know that Hitomi was lost. And the next missions with instruments capable of doing this type of measurements are CRISM in 2023-24 and Athena for the next decade. And then here is when we introduce a new technique to measure velocities in the gas within the galaxy clusters with uncertainty down to 100 kilometers per second. And this technique is done with XM Newton observations, in particular with the EPIC PN camera. So this new calibration method is explained in detail in Sander 2020. I will explain here the main points, but that paper is must read if you want to know in deep how this method works. So first we have here the EPIC and schematic of the EPIC PN camera on XM Newton. So this circle here is the field of view, and we have CCDs. We have 12 CCDs there. These are, here you can see the coordinates of the instrument. And here you can see a feature called Cooper Hole, and I will mention that later. But this is the structure of the EPIC PN camera. With EPIC PN, we have two types of observing modes. One is called full frame or FF, and the other one is called extended full frame. So the point of this method is to use instrumental X-ray emission lines to calibrate the energy scale. That's the point. So we use instrumental emission lines to calibrate the energy scale, and then you can measure redshift of the iron astrophysical line. Here I am showing the spectra of all observations up to 2018 combined. And these lines here are the instrumental lines because due to the electronics of the camera. The main line is Cooper K alpha line, and we also have nickel, zinc, Cooper K beta lines. And here is we distinguish between full frame mode and extended full frame mode. So these lines are used as reference to calibrate the energy scale, and then you can measure redshift. So bottom panel shows image of the detector for different lines. So the first image is for Cooper K alpha. The second image is for nickel K alpha, and the third one is for zinc and Cooper K beta. So you can see that there is a hole in the middle because of this is from the instrument. So because of the instrumental design, which means that because you need the instrumental background to calibrate the energy scale, you cannot apply this method in the center region of the EPIC PN camera. So if you want to analyze a cluster, you need to take offset observations, and that's important. So, but at the end, we can measure velocities down to 150 kilometers per second, and even better, I will show that later. How the calibration is done? Well, I will go a little bit fast here, but it's just 3 steps. The first step is the correction of the average gain of the detector during different observations as a function of the revolution of the instrument, basically. So this is this plot here, and red points and blue points correspond to the different observing modes. You can see that there is a difference in the redshift of the line depending on the observing mode. So you need to correct that. This is the position of the Cooper K alpha line as function of the revolution. The second step is the correction for spatial gain variation across the detector. So you have the redshift on time, and you also have the redshift on the instrument. And then you apply the corrections to each CCD, each pixel. At the end, you will have for each region of the epic camera, and depending on the time, observatory time or revolution, you will have the correction. So that's in general the method. So with this method, Sanders 2020 analyzed Perseus and Coma cluster. Here you can see the cluster, and the colors correspond to different regions for which they analyze the velocity. As I say, in the middle of the Perseus cluster, you cannot obtain velocity because this is the Cooper hole. And also Coma cluster has a hole where you cannot apply the method. So they were able to measure velocities down to 150 kilometers per second. And interesting, for the Perseus cluster, they found a good agreement between the XM Newton observation and the Hitomi observation for the same region. So there is a good agreement there. And for the Coma cluster, they found that the velocity structure is more associated to the subcomponents of the cluster. Also, they found that for Perseus cluster, there is a hint of the spiral pattern associated to gas sloshing. Here you can see these maps are surface brightness in the left, in the middle velocity, and right temperature. And you can see here this hole, as I say, this is the Cooper hole. But in general, the results from the observations are quite similar to the simulations which are above. So these results provide the direct evidence of the ICM sloshing in Perseus cluster. Okay, so that's the technique, and now I want to talk about my work here. The first thing that we did was to perform a new calibration of the epic camera, because now we have 2 years of more observations. In particular, we have 33 full frame, 42 extended full frame, and also because there is a new software from the XM Newton team, and they include corrections for the epic energy scale. So we need to be sure that our correction still applies. So we reduce all the observations in the archive with the new software, and we have redone the analysis of Perseus cluster, and we have found a good agreement between Gatuzz 2021 and Sanders. So here, for example, this is a plot of comparing the Cooper K alpha redshift found, including the new data and the new software, as compared to Sanders. They are quite similar. Here, this is for one CCD for a given position in the CCD. The ratio between the new calibration and the old calibration, the difference are usually lower than 5%. So the new calibration works very well, and we can go ahead with the astrophysical analysis and the science, exciting stuff. So we analyzed 2 clusters. 2 large XM Newton proposal programs were approved, one for Virgo and one for Centaurus cluster. Why those? Well, both are cool core system with AGM feedbacks in the cores, and both shows also charged surface brightness S, which indicates the presence of cold fronts. And cold fronts are also associated with gas sloshing, so they are good samples to measure velocity structures. For the Virgo cluster, and here top right panel, there is a plot of the inner part of the Virgo cluster with the famous jet. There is a central jet and large extended radio bubbles. You can see the bubbles here measuring radio. So there is heavy interaction here between the intracluster medium and the AGM. And for Centaurus, there are 2 dynamic components. So it's a good test to analyze the velocity structure too. So I will show the result for Virgo cluster. This paper was accepted last week, and we are already published in archive. So these are the observations for the Virgo cluster. So this left panel here shows the X-ray emission, the X-ray map. The green circles are pointless sources. We exclude the central part of the cluster too. Here you can see the exposure maps. As I say, we have multiple offset observations because we want to cover the central part of the cluster. That's the strategy in the proposal. These are the exposure maps. You can see here how we have very good exposure times in the central part of the cluster, and lower panel shows the number of counts around the iron astrophysical line. And you can see the holes here, the Cooper holes, where you cannot apply the method, but you can see how in the central part of the cluster we have very good statistics, or at least a lot of counts. So I will mention here what we do in the spectral fitting part, the spectral fitting side. So all the results that I will show later on are obtained from this procedure. So we apply the energy calibration scale to the Virgo observations, to the epic event files in particular. The fits are done in the 4 to 10 kV energy range. Why? Because we are using the instrumental backgrounds instrumental background lines as a reference, and if you move far away from them, the calibration is not good. So that's the reason why we are working in this energy range. So at the end, we are measuring iron K alpha line. The model is absorbing model with APEC plus background. We fix the NH in all these spectra, but as I say, we are not working in the soft band, so the NH is not really important here. So we just fix it to 21 centimeter value. The field parameters are temperature, metallicity, redshift, and normalization. And the background for us is not astrophysical background, but the instrumental background. So this plot here shows a typical spectrum of this analysis. You have the iron K alpha line, which is astrophysical line, is the gas in the cluster. And then you have the background lines as reference. The background model contains a Gaussian for these lines and a power law, and the parameters of the power law were defined by Sanders by their development of the method. And here, bottom right panel, I am showing for different spectra, the numbers here correspond to the different spectra. I am just showing here the variation of the statistic, and just to show that in general, there is a single minimum. The statistic becomes asymmetric. The distribution of the statistic becomes asymmetric far away from the redshift. So I'm just showing here that in general, the redshift obtained are robust, and the statistical uncertainties too. And now I will show the results applying this spectral fitting procedure. So we have created spectral maps. These spectral maps are created following also Sanders 2020 method. You create overlapping regions, elliptical regions. You create multiple regions. For each region, the size of the ellipse is such that you have a minimum number of counts. So at the end, you will create this spectral map with the distribution of a given parameter from the model. For example, velocity, metallicity, temperature, etc. Which means that here I am showing the velocity distribution along the cluster. So in order to be more clear, we are using here a red-blue code, which means that red is redshifted gas and blue corresponds to blue shifted gas, moving away from the, moving to the observer. These contours here correspond to the radio observations, which contains these two jets. And the right panel shows the velocity errors for this spectral map. You can see how you move away from the cluster center when you have where you have more exposure sign, the uncertainties increase. We have found here something interesting. You can see how the gas is blue shifted in this direction and red shifted in the other direction, following the arms, following the jets of underground observations. And it is clear that there is no spiral pattern here, typical of gas sloshing. Here I am showing the temperature and metallicity distribution. We see here how the temperatures tend to be slightly lower in this direction, in the eastern arm direction compared to the western arm. And for metallicity, you can see here how the metallicity increase in regions perpendicular to the soft X-ray arm near the cluster core, most likely indicating the interaction with the AGN. With the best fit parameter from the APEC model, we can create pseudo 2D maps, assuming that the distance are similar between the regions, but you can estimate the density, pressure, entropy distribution of the gas. And we can see that there is high gas density and low entropy around the central region. We can see from pressure, there is a hint for a ring here, external ring of lower pressure. And this ring was also identified by previous analysis of XM Newton observation by Siminescu in 2007. So here we have, after creating the spectral maps, we create manually selected regions to analyze the velocity structure. We have two cases here. One is concentric rings, and the second one is concentric rings, but divide in 4 directions. So the first case, concentric rings, these are the results. Here you can see the redshift, and in the right side in kilometers per second unit velocity. And you can see here the distribution of temperature and the distribution of metallicity as we move away from the cluster core. Red and black correspond to 2 different models because we compare APEC model with this SPECS model that is also used in many cases. And there is a good agreement between the models. So from the velocity distribution here, we have found that there is the innermost region displays velocity similar to the velocity of the central galaxy. But there is an overall gradient in velocity. The velocity increases as we move away from the cluster core, which can be due to gas sloshing. And there are discontinuities in temperature and metallicities that have been identified before us by previous works. For the case two correspond to concentric rings, but divide in directions. The interesting thing here is that if you see in the innermost region, you can see clearly that along the west direction, there is a redshifted gas. We are talking about 1,000 kilometers per second. But along the east direction, there is a blue shifted gas. So again, as we saw in the spectral map, it seems that near the cluster core, there are redshifted and blue shifted gas following the X-ray arms or the radio jets. So this feature is most likely due to AGN outflows. So we go further in this scenario and we study the velocity structure near the cluster core. From the spectral map that I showed before, we select some regions just to be sure about the velocities obtained there. And these are some regions for which we fit the iron line. And it is clear that there is a large difference here between the region number 1 and region number 2, which is more almost 4 sigma of difference between them. So it is clear that there is something something there for real, and probably it's because of the AEN outflows, the difference in velocities. So we also compare radio observations with our X-ray observation. This is the radio image, and we choose regions following the radio structures, like the bubbles, the arms, the lobe, and we measure velocities there. And here I will show the results. The velocities are here. Again, you can see how when you compare region number 1 to region number 2, there is a difference. So there is a difference in velocities there. Of course, we are selecting regions here following radio, so we are not taking into account a number of counts, a good statistic, etc. The uncertainties are large in region 1. Also interesting here, we have found uncertainties for region 3 of 100 kilometers per second, which is very good for our technique. So one interesting thing is that the motion of the gas along the radio arms seems to be opposite, in the sense that in X-ray, the gas is blue shifted when the radio jets are red shifted, and the other way around. This could be a hint of backflows, because backflows have been seen in small scales, and there are also predictions of backflows in simulations in large scales. It could be a feature of that. And then we also analyze the cold fronts, because the cold fronts are related with the gas sloshing of the gas. In Virgo cluster, we have 2 cold fronts, one in the west north side and one in the southwest side of the cluster. So if you look at here at the velocities, you can find that the uncertainties are large for the other region. Well, the velocities tend to be low too. And this is expected if we are talking about gas sloshing, large uncertainties in velocities and low velocities. But in this cold front, the velocity seems to be higher in the outer region and more constrained. But you can see here that still we have close velocities, right? But the point is that this region here, being closer to the cluster core, is more influenced by the AGN. But for example, if you compare metallicity, in both cases, you can see there is a lack of significant metal mixing in both cold fronts. And this is part of the gas sloshing properties. We also analyze the RGS spectra, which is with the RGS spectra in this type of observations, you only can analyze the central part of the cluster. And we measure velocities there. The fit is also a little more different because we have multiple orders in the gratings. But the important thing on this analysis is that at the end, when the velocity that we have obtained with the RGS for the central part of the cluster is in good agreement with the optical velocity of the cluster. And we also analyze the energy profile. To do that, we fit multiple non-overlapping regions. We move away from the cluster core, and then from that we can measure or estimate the contribution of the turbulent velocity of the turbulent energy to the thermal energy. And we have found that for radius larger than 20 kiloparsecs, the turbulent component contribution is lower than 35%, 34%, which is in good agreement with previous estimations. For example, we have Churasov and other works about that. The ellipses here are bigger as we move away because we need to have a number of counts. So that's the reason why the ellipses are bigger. Finally, we have included in this analysis some simulations of gas sloshing. And these simulations each panel corresponds to different angle of view. The thing is that if we compare the simulation with the observations, they are not quite similar. And for simulation, we can see these spiral patterns and not in our observation. But these simulations only include the gas sloshing, not AGN feedback. So it is clear that we need simulations including both effects, at least for a Virgo type cluster. So little review here. We have found hints for both AGN outflows and gas sloshing. In the AGN outflow side, we have change in velocities for regions following the radio morphology. We see how the core front that is closer to the cluster core, the velocities are changing, and the other part has a larger velocity. And the velocity map do not show a clear gas sloshing morphology similar to those obtained simulations. But in the gas sloshing side, we have found an overall gradient in the velocities. We have found that for the northwest core front, the velocity is close to the rest frame, and we have high uncertainties there, which is kind of expected from simulations. And there is the lack of mixing, metal mixing in the core fronts. Then we have also Centaurus cluster observations, and we apply the same method here. These are the image. In this case, white contours correspond to X-ray contours. Again, you can see here the exposure maps. We have covered the central part of the cluster with multiple offset observations in order to apply the method to the central part. And here you can see the number of cones in the area K alpha line region, spectral region. We did again spectral maps for Centaurus cluster. Here you can see the temperature distribution, the metallicity distribution, and the velocities. Again, blue correspond to blue shifted gas, red correspond to red shifted gas. Temperature and metallicities are similar to Chandra results, but one thing to take into account is that we are modeling the high energy band from 4 kiloelectron volts to 10 kiloelectron volts. So there is a lot of lines that we are not measuring there. So the temperature and metallicity are most likely over or underestimate. But the important thing for us here is the velocity, which is very well estimated with our method. There is a complex structure near the cluster core. We have high blue shifted regions, and we are analyzing these results. Now, we also did an analysis of concentric regions just to see how the velocity structure change as we move away from the cluster core. There is a hint for an overall gradient in velocities, which could be also associated to gas sloshing. And we have found also temperature discontinuities, which have been also observed in Chandra observations. Interesting, we have found for some regions with really good data, really good statistics, uncertainty is down to 90 kilometers per second, which is fantastic for XML Newton. We also divide these regions along 2 directions to see if there are any kind of symmetry or not in the behavior of the gas. Definitely it's a complex velocity profile. Although the temperature is similar in both directions, but the metallicities, you can see here how the metallicities increase as we move in the eastern direction. And also we create manual regions. Why? Because we know that Centaurus contains a component, and we want to see if the velocity structure is more associated to the subsistence than to gas sloshing, for example. So here the size of the regions are chosen in a way that we have a minimal number of counts and the same statistics everywhere. You can see here the distribution of the velocities, and we have found hints of that the gas close to each one of the subsystems moves with a velocity associated to such a system. So in Centaurus, we have the influence of both the gas sloshing and also the dynamics of the subsystems there. So we last year we are cold fronts. For Centaurus we also have cold fronts. We have at least 3 cold fronts, and we analyze the velocities there. The uncertainties are large for some of the regions, and in general we cannot identify a change in the velocity. This could be associated with gas sloshing too, because if you compare temperature and especially metallicities, you can see how the metallicity changed when you move from one region, from inner to other region in the cold front. So this is an indication of the gas sloshing. So last year, that was for Centaurus and Virgo. So last year we applied for a large observation for a large proposal, for a large exomoon proposal to observe the Ophiuchus cluster. Why this cluster? Because it's nearby. It's the second brightest cluster in the 2 to 10 kiloelectron volt energy range. This top left panel shows the observation in the archive. So we have already observations there. Top right panel shows a binning of the image just to see the number of regions that we can obtain to fit there. But as I say multiple times now, we have a hole in the middle and we cannot measure velocities there. So we propose this green, yellow, blue, and red observations to cover the entire cluster. This is a large proposal of almost 700 kiloseconds. Ophiuchus is a massive and relaxed cluster, so it's interesting to add this to our sample. Chandra observations have revealed the existence of cold fronts, so maybe gas sloshing is there, feature for gas sloshing. And well, the proposal was approved last year, and the first observation were done 2 days ago. So we are pretty excited about that. Yes, in the following weeks, the rest of observations will be done, and we will see what we can measure there. We have more work to do. Of course, we are looking for offset. We need observations taking offset to apply the method. So we are looking in the archive for such clusters, and we have found some candidates. But in general, we need more exposure time. So we are looking forward to apply for more observational time. Regarding method, there are other instrumental background lines that can be used to apply the method, and these instrumental backgrounds are in the center of the detector, like titanium, for example. Of course, these are weaker when compared to copper, but if we can apply this method to the central part of the detector, we have all the archive for us. So that will be exciting, and we are discussing about the possibilities to do that. Because, for example, exomoon epic camera has a large field of view. It will be great if we can do this to the archive. From the eROSITA point of view, I am working here at MPE. Of course, we have eROSITA every day. And the question is, can we apply this to eROSITA, for example? Well, in principle, the background lines are there, but the effective area is worse than for exomoon. But we are discussing this too. So yeah, this lead to my conclusions. I hope I have convinced you that the velocity structure in galaxy clusters is important. We can measure velocities with uncertainties down to 100 kilometers per second with X and Newton. It's fantastic. Our analysis of Virgo cluster shows features or properties for both aging outflows and gas sloshing. Our preliminary analysis of Centaurus cluster shows hints for gas sloshing, but also for the dynamics of the subcomponents in the cluster. We already have X Newton observation for the biggest cluster. We will have results soon, I hope. And from the simulation side, we need more simulation because for example, for Virgo, we need to put together AGN outflows, gas sloshing, and everything to compare with other observations. So I think it's pretty exciting, this research area for the future. And that's it. Thank you.
All right, thank you, Efrain, for a great talk. If there are any questions, please raise your hand and we can call on you, or if you want to type it into the chat window, that's fine too. Come on, folks, don't be shy. Okay, we've got one from Paul Nelson. Can you comment on the errors for Centaurus?
Sorry, say hey, sorry. Wait, is it the chat? Okay.
Yeah, it's in the chat.
Can you comment? Yeah. Let's go. Well, again, the uncertainties depend. We have systematic uncertainties, of course, but in general, we have found that the uncertainties depend on if you have a strong iron line because for some regions and for some clusters, depending on the temperature, the iron line is weak. If you have a strong iron line and you have enough statistic, so for example, for the central part of the cluster, in some cases we have found some spectra with amazing statistics, and you can find velocities, uncertainties down to 90 kilometers per second. But of course, in some cases, we are talking about uncertainties of 200, 300 kilometers per second. So that depends. But for some regions, we have found very low uncertainties, which is great. But for example, as I show here, there is also a game between the statistics, the exposure, but also the physics behind. Because for gas sloshing, we expect some high uncertainties because as I show in simulations here, you can see here how the distribution of the velocities is. So if you select a large region, you will have there large uncertainties regarding the velocity. So yes, so for some region we have very low, and for some, no.
All right. We have a question from Charles Romero. The reported possible backflow velocities for M87 outflow regions are along the line of sight. Is the expectation that if they are indeed backflows that they would be radial? And if so, what is the angle of inclination or resultant 3D velocity? Is the resultant velocity expected or not?
That's a good question. Well, one thing that is this, as you say, this work is only for velocities in the line of sight. We don't have tangential velocities here. So regarding the backflow, we just mentioned in the work that there are definitely there are measurements of backflows in the jets in Virgo cluster, but in very small scale. We are talking about hundreds of parsecs. And simulations predict that these backflows are also in large scales. But as you say, we are talking here about one dimension. Is really, we cannot create yet a complete modeling of the backflow there. So yes, but it's interesting. I mean, we could work more on this, right? And the velocities expected or not? Yes, there are for simulations from the, I mean, the range of the velocities in the simulations are somehow expected. We are talking lower than 1,000 kilometers per second. Yes.
All right, do we have any more questions? Okay, if not, let's thank our speaker again for a great talk. And we'll see you all next week.
Thank you.